So yeah, just to kind of go over what I said again, because I'm recording now. So for chapter 1, make sure you know significant figures, isotopes, average atomic mass, and electron configurations. For unit 2, make sure you know the difference between metals, nonmetals, and semimetals. That's extremely easy. I'll show you that in a minute. Know the difference between a group and a family and a period. Groups and families are the same thing. And then know some trends, density, ionization energy, and atomic radius being very important trends. And unit 3. So unit 3, like, it doesn't look like there's a lot here, but there is a lot here. Unit 3 is definitely one of the units you want to study. Unit 3, you have to know naming and formulas. You need to know naming for ionic compounds and covalent compounds. You won't really see much about acids and bases, but you definitely need to know ionic and covalent compounds. You also, very important that you know this, the electron dot diagrams, Vesper shape. I think I'm going to do a practice problem on that today as well. Like chapter 5 is a very important chapter, but we literally just finished it. I mean, I finished chapter 5, I think, on Monday. So I think today I would really like to look at electron dot diagrams, Vesper shapes, polarity, and intermolecular forces. That's definitely one of the questions I want to do with you guys today, because you will certainly see that on your final. Okay, now unit 4 looks big, but it's really not. Well, first of all, if we go back up here, unit 4 is worth 9, like less than 10% of your final exam. So it's not actually worth a lot. But the concepts you learned in chapter 4, you will need to know for chapter 5. So what did you learn in chapter 4? Well, you learned how to calculate molar mass, you learned how to calculate moles, particles, molarity, and then we did percent concentration and ppm. And you guys did this all in the lab as well. Now, you don't need to study your labs, don't worry, but you guys have definitely had some practice in chapter 4. Again, it looks like it's a lot, but it's really not that much. The reason chapter 4 is so important is because it brings us into chapter 5, which is probably your most important chapter to study. We looked at balancing chemical equations. We looked at predicting chemical reactions. We looked at redox reactions, total and net ionic equations. And then finally, stoichiometry. Stoichiometry was that stuff about mole ratios that we did on like Monday and Sunday, and then we did it last week as well. So stoichiometry is a direct follow-up from chapter 4. So again, I've said this before, but if I were you guys, I would focus on chapters 3, 4, and 5. Then I would worry about chapters 1, 2, and 6. I would probably save chapter 6 for the end. I would definitely focus on 3, 4, and 5. All right, so for chapter 6, realistically, I can explain chapter 6 pretty easily. This is actually your multiple choice. You have one question on your final exam about gas stoichiometry. That would have been the last, I guess second last, not last. Sorry, the second last problem we did. In unit 6, unit 6, that is a gas stoichiometry problem. So again, if you remember class yesterday, we found the moles of a chemical, we used the mole ratio, and then we answered the question by calculating the volume of that chemical. So this is this is honestly a really good study guide. If you know everything on this study guide, I mean, you're guaranteed to get, I mean, a 90, 95, even 100 on your final. This is literally everything you need to know. Oops, sorry. There are some theory questions in your multiple choice, so you you will probably want to look at your worksheets. Your worksheets are really good. But other than that, yeah, this is basically what you need to know. Yes. Okay. So I'm looking at the questions. I'm going to answer Asil's email question in a minute, but Abdullah asked the question, are molarity and concentration the same? Yes and no. Now that sounds really confusing, doesn't it? Concentration, so C, concentration is a measure of how much solute you have in a solvent. In chemistry, typically, we measure concentration as moles over volume, and we call this molarity. So yes, molarity is the same as concentration. However, there is also percent concentration, and there's also ppm, which we certainly use in chemistry, but you would use percent concentration or ppm more in real life / engineering or the medical science schools. So if you're in medical science, you're definitely going to use ppm. If you're in engineering, you would probably use all three of these. You would use molarity, you would use percent concentration, and you would use ppm. So molarity is a measure of concentration, but there are three types of concentrations you guys are expected to know. And that's not to confuse you. Like we're not trying, or I'm personally not trying to give you guys too much to memorize, but honestly, if you're an engineer, your medical science, your occupational health and safety, or environmental health and safety, you're going to use different numbers, and they would include molarity, percent, and parts per million. So sadly, you have to know all three. Okay, this is Abdullah asks another good question, and I actually had this question this morning in the other group. There are technically no definitions. Now, let me explain. In your multiple choice, you might see definitions. So let me give you an example. What is mass number? So, okay, what is mass number? The answer to that is mass number is the number of protons added to the number of neutrons. So in the multiple choice, you might see some definitions like that. You know, what is mass number? Which group are the halogens? Halogens are group 7A or group 17. What are valence electrons, right? That could be another one in your multiple choice. Valence electrons are the outermost electrons in a atom or element. But there are no definitions that you have to write. So in the constructed response, in like the short answer section, section B, there are no questions that say define valence electrons or define immiscible, define soluble. It's not there. So you guys do not have to define anything, but you will be expected to find them in like a multiple choice. Does that help? You know what I told my class this morning, like you don't have to memorize definitions word for word, just know how to pick them out of a multiple choice. Perfect. Guys, I know this might sound like every teacher says the same thing all the time, but this is a pretty easy exam. It's pretty straightforward. There's no surprises. If you look at your worksheets, you look at your quizzes, you're fine. Like your exam is in a few days. Don't rewatch every video. Don't read every slide. What I would do is do your worksheets first. Then you could try some of the quizzes on D2L. You could look at old quizzes. You could look at some of the new ones I just uploaded just for practice, but don't watch every YouTube video again. You'd never have time. You go crazy. Okay, so let me look at Asil's question for you. I don't feel like I'm saying your name right, but anyways, let me open that up. And actually, Asil, I didn't really even look at, I did look at your email, but I didn't look at the question. I know it's in chapter 2, and you mentioned for me to look at sections 2.2 or 2.3, and then you mentioned what about 2.4? The question that you did share with me, the picture, is good. It's really easy to explain. So let me open this up. Actually, I guess what I'm going to have to do, I can't open up your email um, easily. So the question that you asked was question number 1 on worksheet from 2.2 and 2.3. So let me open that up and I'll share my screen. Just give me 1 second here. I'll open that up. Oh, okay. My computer is being really weird, but here it is. Okay, so let me share my screen. I'll open that up for you. So here's my screen. Obviously, there's nothing here. I'm going to go to your D2L, log in. Ooh, I got another good question here in the chat. It was a private message, so you guys might not see that. The question was, do you need to memorize the elements' names? And that's a perfect timing because I can show you. So chemistry 2. So, okay, I'll go to a seals question in a minute, but what about the element names? Do you have to memorize the element names? The the bad answer is yes. You do have to memorize element names. That's crazy. However, you should have known, or you should have been I mean, this whole semester we've been doing element names, so we've had months of practice. Okay, obviously there's 118 elements on the periodic table. You do not need to memorize 118 names, guys. I promise you, there are elements on that periodic table that I don't know the name of. I've never used them in my life. So, some of the radioactive ones or the ones in the lanthanides or actinides, I've never used them in my life. So you don't have to memorize every element. The elements that you are expected to know, you can find here. Click on content and click on, sorry, not that. Sorry. I got to erase this too. Sorry. You'd think I'd be real good at this. Okay, here we go. The chemicals you need to know, you would find in content. You would click here, and then you would click here. By the way, guys, this data booklet is given on your final exam. I had a couple students this morning ask me, do we get the data booklet? Are we given a formula sheet? Can we bring our own data booklets? The answer is yes and no. You are definitely given a data booklet, but no, you cannot bring your own. You have to take a new clean data booklet just so that there's no writing on your data booklets. Okay, the data booklets are clean, they're printed new, they're not used, so you don't have to worry about COVID or anything like that. But yeah, your data booklets are given. Now, to answer, I think the question was from Ahmed. What elements are you expected to name or know? Now remember, naming is very, very important on your final exam. Like I would say maybe 8 or 9% of your final is from naming. And you can't name a chemical if you don't know the names of the elements. So this sheet here, this is all of the elements you're expected to know. It's on 2 pages. It's written very big, of course, but these are the elements you should know. You definitely need to know elements 1 to 20, and then it gets a little weird after that. There's a select few that you need to know. A lot of them are metals like chromium, manganese, iron, nickel, zinc, germanium, tin. Good old tin is weird. Oh, actually, let me show you guys something. I just remembered this. I got a little hint for you guys. I got a little secret inside information here that might help you with naming. Just imagine this document here. You don't know the names of all your chemicals. I'll whisper this. I'm gonna give you guys a little way to cheat, to figure out the names of chemicals without having them memorized or written down. Go to your data booklet. Your data booklet is amazing. Okay. You have polyatomic ions. You'll definitely need these for naming. Obviously, they're all written. You don't have to memorize these. Your solubility table, the Vesper model, which I'm going to do a review of in maybe 10 minutes. But look at this table. Whoops, I didn't mean to do that. Look at, sorry. Look at this table here. I'm trying to be sneaky and cool, but it's not working out. This is your activity series. You guys need your activity series for chapter 5 when you're doing a single replacement reaction. But look at this. All of these elements are named for you. Now, obviously, this isn't every element. For example, there's no non-metals here, but you guys should be pretty good with non-metals. I mean, O is oxygen, N is nitrogen, C is carbon, Cl is chlorine, very easy. But if any of you are struggling with naming, all of the metals are here, even the weird ones, like tin. You know, tin isn't T or Ti, it's Sn, and that's from the old Latin name. Bismuth is Bi. Mercury is Hg, platinum, Pt, gold, Au. So and again, this is really only for the metals, but if you don't know the name of a metal, it's here. Or I should say the element, the symbol for a metal, it's all here. So Ahmed and other students nervous about this. Honestly, it's here. Every metal that you need to name is here. All right. Now, let's get to a seals question, and then I want to definitely would like to do with you a Vesper intermolecular force type of question, and then I'll open this up for anybody who has any more questions. So a seals question that I got this morning in email. And if you guys personally have any questions, you can let me know. Send me an email. I'll get back to you as soon as possible. Her question was from this worksheet, and it was question number 1. So question number 1 says, check all the boxes that are true for each element. We have bismuth, germanium, iodine, astatine, selenium, and gold. This is actually a pretty tricky question because you have to look at your periodic table and figure out if it's a metal, non-metal, or semi-metal. This semiconductor, these are pretty old worksheets. You don't have to worry about semiconductors. It's not on your final or anything like that. The only really semiconductor that I can think of that stands out is silicon. That's not in chemistry 1120. So who cares about the semiconductors? I'm more concerned with this table. So what I'm going to do, I'm going to clear my screen. I'm going to open up your data booklet. Now, this is going to look a little small. There's not much I can do about that. So here we go. Let me share my screen. All right, so you guys on the screen right now, you should see the worksheet, and you should see about half of the periodic table. I think I could even zoom in a little more. There we go. Okay, bismuth, Bi. Okay, so let me get my pen here. Bi is right here. This is a definitely a metal compound. It's not a non-metal. Let's get the non-metals out of the way first, and the metals. So let me circle all of these. So I have bismuth, I have germanium, I have iodine, astatine. You'll notice for astatine, selenium, and bismuth, we give you the atomic number. That's if you don't know the name or the symbol of these, the number will help you find them. So Z is my atomic number. Where's selenium? Selenium 34. I got astatine circled, gold 79. Okay, so first things first. If it's not literally next to the staircase, meaning like this guy, this guy, this guy, this guy, if it's not next to the staircase, it's a metal or a non-metal. Chemicals that are to the right of the staircase, so in this case, selenium and iodine. Let me pick a different color here. Selenium and iodine, these are not on the staircase, so these would be non-metals. So selenium, non-metal, iodine, non-metal. Now, the same thing goes for, I'll pick a different color. Let's pick, what am I feeling here? Let's go orange. Gold is not even, and bismuth. So gold and bismuth are also not on the staircase. They are to the left of the staircase. They would be metals. So gold and bismuth would be metals. So now I need to look at the chemicals that are on the staircase, meaning they're touching that black line. Let me clear some of my writing here and explain that. Oops. Okay, sorry, I'm just going to clear my writing here. Now, when I say on the staircase, what I mean is it literally has to touch the staircase. So boron, silicon, germanium, tin, tellurium, astatine, polonium. These are semi-metals. The only exception to this list is aluminum. Aluminum is a metal, right? That's the only element here that touches the staircase that is not a semi-metal. Aluminum is a metal. Okay, that's the only exception. So let's go back to green here. Germanium, that's GE, is a semi-metal because it's on the staircase. And astatine, this guy down here, this is on the staircase, so this is a semi-metal. Don't worry about semiconductors. I don't know why that's there. I didn't make all of these worksheets. Some of them I made, some of them I didn't, but don't worry about semiconductors. The only semiconductor I can truly think of is silicon. And that's why, you know, it's called Silicon Valley. This is definitely a semiconductor. I don't know, my pen is going a bit weird there, but anyways, there you go. All right. Yeah, I mean, like it kind of depends. Kind of like there's it really depends on what book you're looking at or like what information you're looking at. The easy answer is anything that touches the staircase you could call a semi-metal. The only element that touches the staircase that is definitely not a semi-metal is aluminum. There's a lot of research about this and a lot of different kind of information you can find, but nobody would ever say aluminum is a semi-metal. Everything else that touches that staircase, silicon, germanium, astatine, anything, is a semi-metal. By the way, guys, I don't think that this is on your exam, so it's not really a big deal. The other question I had this morning from a seal was section 2.4. Now, I don't even know what this is, so let's have a look. Section 2.4, it's probably ionic trends is my guess. Yeah, so section 2.4 is all about ionic trends, the density, the atomic radius, electron affinity, ionization energy. This is straight, actually, this is a really good practice worksheet, for example. You will see a question like this on your final exam where we'll give you like a blank periodic table and you'll have to like pick, you know, which element is in the halogens, which element has the largest atomic radius, which element, you know, so this is a really good practice problem. Now, I don't want to do the worksheet here because this honestly is definitely a worksheet you guys should practice, worksheet 2.4. So what I'll do is I'll go back to my notes. Let's do that. And I'll kind of explain some of these ionic trends in your notes. Give me 1 second here. I'll open it up. One of the only chapters where you might want to look at your notes is chapter 2, because you don't really need to watch a video about chapter 2. What am I doing here? Share my screen. All right, so chapter 2 is on the periodic table. This would be a good chapter to read. Very good chapter, but it's not worth very much on your fund. Well, I guess it's worth about 15%, but let's look at some of your periodic trends. There are 4 trends that we covered in class. So first of all, the density. The density is the mass of an object divided by its volume. So the trend in density is, as atomic number increases, so does density. Boom, that's it. So if you had to pick an element that was dense, whichever element has the highest atomic number, that is the most dense. Easy. All right, let's go to my next trend. Atomic radius. Well, the atomic radius is the size of the atom, and there's a lot of information here that you guys don't need to know, like the difference between bonding atomic radius and regular atomic radius. Don't worry about that. All you need to know is the trend, and the trend in atomic radius is this. Atomic radiuses, or atomic radii, increase from right to left, and they increase from top to bottom. So if you look at this picture here on this slide, you can see that typically, and now this is just a trend, it's not always true, but typically on the periodic table, trend, the atomic radius, the size of the atoms, increases going this way. It increases going down and going left. So the biggest elements would be here, and the smallest elements would be up here. That's atomic radius trend. So again, atomic radius gets larger as you go down a group and left, down and left. Okay, this you don't need to know this. Atomic radius depends on that, blah, 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 blah. Doesn't matter. You just need to know the trend. Okay, ionization energy. This is the energy it takes to turn something into an ion, meaning the energy it takes to remove an electron. Things become ions when you remove electrons. So let me just see if I have a summary of this. Here we go. Ionization energies increase as we go across a period, across meaning left to right. And ionization energy decreases as you move down any group. So it basically increases as you go up. It decreases as you go down. So that's ionization energy. Those are those trends. And then finally, electron affinity. Electron affinity is the same method as ionization energy. It increases as we go from left to right. Okay, and actually what I can show you, the easiest way to do this or to think about this, do I not have it in here? I'm pretty sure I put this in my notes. Hold on, give me 1 second. If it's not there, I'm going to show you something in a minute, something you might want to take a screenshot of. Okay, hold on, let me open up my notes. There's a slide in my notes that I don't think is in this PDF. Just give me 1 second here. Yes, okay, this is it. This slide, let me share my screen. Let me show you. This is in my notes, in my PowerPoint. So if you open up the PowerPoint, you'll see this. This is basically the summary of all of the ionic trends you need to know. I mean, this is it. If you just had to know one thing from ionic trends, it would be this slide here. Okay, so ionization energy, electron affinity increase as we go up, and they increase as we go right. Now, the ionic radius or atomic radius is the opposite of this. The atomic radius gets smaller as we go across and we go up. And I mean, yeah, really, that's it. That's all you need to know about ionic trends, this slide right here. I'll clear my drawings if you guys want to like take a picture of that, but it is in my PowerPoint. So if you guys open up my PowerPoint for chapter 2, this is really important. All right, let me check the questions. I got a few questions. Well, 2 questions. Okay, so guys, I'm going to answer the 2 questions I have here, and then I just want to show you kind of one VSPR example, just to remind you of chapter 3, and then I'm personally done, but if you guys have questions, you can ask me. So let's look at the 2 questions. These are both private messages, but I'm going to say your names. Don't get mad at me. Ahmed asks, if you do the worksheets, will you get full marks? I'm going to say no. Full marks is 100. If you want 100, you literally have to know everything. Like to get 100, you need to know sig figs, you need to know terms, you need to know everything. So, you know, worksheets won't cover every topic ever. But if you know the worksheets, you will be like, if you have no problem with the worksheets, you'd be guaranteed to get an A. Right? But for full marks, you need perfection. I don't even know if I would get full marks if I did this test. I'd make a mistake somewhere. Although I have been teaching here for 11 years, and there are always students who get 100. So it's not impossible to get 100. There's always students that get 100. But if you only knew the worksheets, I don't think you'd get 100. But you definitely get an A. Abdullah in a private message asked me this question. I only see, oh wait, maybe there's 2. I just got to scroll down. Okay, so one question that I'm getting asked is about electron configuration. So let me take a minute to explain electron configuration. Where do I want to go for this? I guess I'm going to go to your periodic table. Just give me a second here. I got to find your periodic table. Hold on 1 second. My stupid computer. I have too many tabs open, so I can't see everything. Just give me 1 second to clear this up. All right, so again, this question was about electron configuration. I'm just going to open up my, if I can, here we go, finally. Your data booklet. Okay, so electron configuration. Let's just take something easy for right now because I'm running low on time. Let's take sodium. Okay, so there's 2 ways to write the electron configuration for sodium. One, there is the expanded or regular electron configuration. So we have 1s1, 1s2. Okay, and then we have 2s1, 2s2. Then we have 2p1, 2p2, 2p3, 4, 5, 6, 2p6. And then finally down here, we get 3s1. This is called the electron configuration. I think we did this in chapter 1 or chapter 3. I can't remember. I teach way too much chemistry courses, but this you did in chapter 1 or 3, I do believe. Now, the question I just got was, what about this idea of condensed electron configuration? Well, there's a way to do this that instead of writing all of these numbers, I can write the condensed electron configuration for sodium like this. Okay, this one right here, this is called the condensed electron configuration. So what I do for this one is I just go right to neon, okay, chemical number 11. Let me clear my little drawings here. So I go to chemical number 11. I just call it neon, and then I can skip down here and write 3s1. That would be the condensed or shortened electron configuration. All right. Okay, and the next question I have, sorry about my dog there.
Mister?
Yes?
So I can do both?
Um, yeah, hold on 1 second. Let me grab my dog, but I'll answer that in 1 second. Whew, okay, sorry. She's been outside because it's so nice out today, but there's another puppy out there and she goes crazy. Anyways, so 2 questions. I just got that question in the live chat about electron configuration. You have to do whatever, like if it was a multiple choice, you have to do whatever we ask for. So if we ask for the electron configuration or we ask for the condensed, you have to answer it in the multiple choice correctly. If we ask you in a short answer question, you can give me whatever you want. Okay, if it's a short answer, like fill in the blank, you can write whatever you feel comfortable with, condensed or regular. All right, let me go back to the chat. Abdullah, this is a really quick question. How can you know if it's natural sulfur or octasulfide? Octasulfide is not a chemical, doesn't exist. Sulfur is always S8 when it is by itself. Natural sulfur is S8. Okay, I can clear my slides here. Natural sulfur, we wouldn't call it octasulfide. It's just called sulfur, and it's always S8. Okay. Yeah, that's the answer to that question. I know what you mean, octasulfide S8, but if it's by itself, it's always S8. Okay, guys, so it's 4:20. I know some of you might want to go. It's Thursday afternoon. Guys, I want to show you something. I have a little present for you or a gift for you, and it's kind of because I missed something when I was teaching this to you. So before you go, I would love to show you a Vesper problem, but I have a little gift, and I gave this gift to the class this morning, and I can take my time on it. I'm not in a rush, but if any of you want to go or you need to go, I want to give you a present, a gift, because you've all been such wonderful students. At the end of chapter 3, there was a section on acids and bases that we didn't cover. We didn't have enough time. We ran out of time for the acids and base chapter, and then I moved on, and then next thing you know, it's December, and we don't have time. There is a multiple choice that I want to show you, and I'm going to show you this right now. This multiple choice is on your final, and we did not talk about properties of acids in class. So this is a question straight from your final exam. This is question number 17, and it's asking what statement about acids is true. Now, you guys will look more into acids in Chemistry 1121, but when the exam was printed, I didn't know that this was going to be there, and it is there. So the question is, which of these statements about acids is true? This is, as you can see from the top of the page, guys, this is your final. Okay, so this is question 17. And it says, which statement about acids is true? Do acids feel slippery? Do acids have a pH of less than 7? pH is the term that corresponds to the strength of an acid or base. Do they taste bitter, or do they change pH paper a different color? The answer to this, and my gift to you, is that acids, they definitely don't feel slippery. Acids also don't taste bitter. When you guys eat an acid, think about lemon or vinegar, or I don't know what else acid you would eat in everyday life, but like lemon juice, lime juice, so vinegar is acetic acid. They taste sour. They definitely don't turn pH paper blue. The answer to number 17 here would be B. Acids have a pH of less than 7. Bases have a pH of greater than 7. And I do apologize that I didn't get to that this semester. We ran out of time, but bases have a pH of bigger than 7. acids have a pH smaller than 7. So there you go, guys. There's a question for you. When I showed this to the class this morning, I had one student say, "Oh, well, I get 1 out of 100 at least." So there you go. I apologize we didn't cover this topic, but there it is. Acids have a pH of less than 7. And I mean, it's definitely not time, or it's no time to teach you something new. So you don't really have to worry about what pH means. But for any of you guys going on to Chemistry 1121, Chapter 4, and by the way, I am teaching 1121 next year, so some of you might have me again. Chapter 4 is all about this, and you'll learn a lot more about acids and bases in Chapter 4. So anyways, there you go. There's a question for you that I didn't get to cover, sadly. Yeah, I made the paper. I zoomed in a lot to the paper so you guys couldn't see everything. But Abdullah, you said B. Yeah, that's really good. That's excellent. Well, somebody says in the chat, give you another question. I think I could give you another question, but I'll do this a little differently. So just give me 1 second here. I'm just going to share your data booklet here. And let's look at another question. But what I'm going to do instead, like honestly, I'm not really supposed to be showing you guys the final, so I'll get in kind of trouble here. But I can definitely give you a question in part B that we can look at together. So just give me 1 second here. I really today want to do one with you about VSEPR. I think it's been a long time since you guys looked at the shapes of molecules. So let me just see. What can I do for you? Okay, this is good. Okay, I'm going to do this question with you, and I'm going to kind of I'm going to add a twist to this question. So let me open up. Sorry, I'm just going to write this down. Okay, so I'm going to add a little twist to this question. I'm going to make it a little harder. I'm going to add something to this. So let me open up a PowerPoint so I can have a blank slide here. And I will show you new share. Okay, so guys, on your final exam, you also need to know about VSEPR. Oops, forgot my P, meaning like the shape of molecules, the name of the shape, and the three-dimensional sketch. So let's look at, wink, 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 let's look at 2 different chemicals. But let's make this question a little harder. Let's amplify this a little bit. I want to name the shape. I want to sketch the shape. And I also want to talk about intermolecular forces. Remember intermolecular forces. So London dispersion, dipole, dipole, and hydrogen bonding. All right, so let's look at these. So what I want to do is I want to first draw the Lewis structure for these shapes. So the Lewis structure, or the electron dot diagram, sorry, for these shapes. So here's my electron dot diagram for these shapes. Now, you guys did this way, way, way back in lab 6, which was like a month ago. But these are what I would call my electron dot diagrams. So on your exam, wink, 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 you guys will be expected to do 2 things. You will be expected to name the shape. You know, is it bent? Is it linear? Is it trigonal planar? And then you will be expected to sketch the shape, meaning draw it in 3 dimensions, which is way easier than it sounds. So when you're naming shapes, or when you're trying to figure out the shape of a compound, look at the central atom. My central atom, my oxygen, let me get my highlighter here. Whoops, sorry, I didn't mean to do that. Let me get my highlighter. Okay, look at the central atom and write down how many lone pairs you have and how many bonds you have. So here I have 2 lone pairs. And here, oops, not 0. Here I have 2 bonds. Okay, let's look at the methane. So for methane, I have 0 lone pairs, and I have 4 bonds. All right, so I'm looking at 2 lone pairs and 2 bonds, and I'm also looking at 0 lone pairs and 0 bonds. So I go to my data booklet, I go all the way up to this graph. This is in your data booklet. This is on page 4. This is the only page, the only part you'll need to know from this page is the top part. Okay. So in chemistry 1120, we only deal with the top of the page. So I have 2 and 2. That means it's bent and would look like this. Okay, I'm just making a little sketch here on my little notebook I have, so I draw it correctly. When I was in university, we drew these a little different, which is why I'm making a quick sketch here. Same thing, actually, just there's a few minor changes. So I'm just making a little sketch. Okay, so guys, the other chemical, so this would be the OF2. I have 2 bonds, 2 lone pairs. The shape would be bent, and it would look like this. The other shape I have would be CH4. 4 bonds, no lone pairs. The shape is tetrahedral, and this is what he would look like. Now remember, wherever you see an A would be your central atom. Wherever you see an X, those are just other atoms. And then wherever you see E, those are your lone pairs. E stands for electrons. All right, so let's go back to my notes. Just give me a second here. I got like 1,000 windows open, guys. It's so hard to navigate. So this shape would be, let's pick a different color. This would be bent. This would be tetrahedral. Okay, and then I would just make a little sketch. So this would be O. And guys, I'm just following, oops, not X, just following what my data book tells me to do. So I would put my F's here. Then I would have like a little wedge and some hashes. And then I would put my lone pairs here. You could call this E if you wanted, by the way. Right, you could put an E there. I'm a fan of drawing the lone pairs. Okay, this guy, methane, would look like this. So methane is tetrahedral, and it would look like this. We would have C, then you would have H, H, and guys, I'm not even thinking, like I'm not applying anything here. I'm just copying from my data booklet. That's all I'm doing. I'm just copying whatever the data booklet tells me to do. All right. Cool. Now it's 4:30. I know we're running out of time. Well, I mean, I can stay for a little longer for sure, but one more thing I want to talk about, and let me just check the chat. Okay, ooh, I got a big question. Oh, okay, Abdullah, that's a really good question. So Abdullah, if you can hang around for a few minutes, let me get to this. And a CLU said, can you show us another question that's not multiple choice? This is another question that's not multiple choice. Wink, 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 wink. Now, what's not part of this question, but what you might need to know for another question is the intermolecular forces. Okay, intermolecular forces. Just remember that there are 3 intermolecular forces. There are London dispersion. Every chemical on Earth, every molecule on Earth has London dispersion. Oops. 2, there's a force called dipole. This is for polar things. And then 3, there's hydrogen bonding. Now, hydrogen bonding happens when hydrogen is bonded to F, O, or N. Okay, London dispersion, everything has it. So those are pretty easy, right? London dispersion. Does the molecule have London dispersion? Yes. Yes, it does. Everything has London dispersion. Does the molecule have hydrogen bonding? Well, is there a hydrogen bonded to F, O, or N? Remember, hydrogen bonding is fun, F-O-N, fun. Neither of these in this example have hydrogen bonding. No hydrogens here are bonded to F, O, or N. So these molecules, they definitely have London dispersion. Okay. They do not have hydrogen bonding. None of them have hydrogen bonding. So the next question is, are they polar? Do they have dipole-dipole forces? Well, the way that, and this kind of goes back to the question I have in my chat, which I'll answer in 1 minute. I think it was Abdullah who asked that in the chat. Yeah, Abdullah. How do you know if something has dipole-dipole? Well, you need to figure out if it's polar. A chemical is polar, and you can see this in my notes. This is back in chapter 3. A chemical is polar if it has 3 different elements in the compound, like 3 literally different elements. So neither of these examples on this page has 3 different elements. I have oxygen and fluorine, and I have carbon and hydrogen. I would need a 3rd element in one of these, like a chlorine or something. The other reason, or the other way you know if something is polar, is if there are lone, this is the big one, wink, 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 is there lone pairs on your central atom? And if you look at OF2 here on the left, this is polar. And I know it's polar because it has 2 lone pairs on the central atom. Any central atom that has lone pairs is polar. Is methane polar, this chemical over here? No, it's not polar. There are no lone pairs on that chemical. And the last way that you can tell if something is polar is if there are no central atoms. So it's just like 2 chemicals bonded to each other, H bonded to H or H bonded to F. If the elements are different, it would be polar. So you definitely want to check that out in your notes. It's in chapter 3. And OF2, I don't know if I'm understanding the question in the chat right, but there's no hydrogen bonding in either, in either of these. There's no hydrogen bonding because none of these chemicals have a hydrogen bonded to N, O, or F, or FO or N. So OF2 does not have hydrogen bonding because there's no hydrogen. If there's no hydrogen bonding. Can't happen. Whew, okay. Sorry, I'm getting tired here. Yeah, so Abdullah, I have 2 questions from you, so let's look at that. Abdullah asks, what about HF? Well, HF obviously has London dispersion. It's definitely polar because it only has 2 atoms and they are different. And it definitely has hydrogen bonding because hydrogen is bonded to F. H2O is another famous chemical, guys. H2O has London dispersion. They all do. It is polar because there are lone pairs, and it has hydrogen bonding. So HF and H2O are 2 very classic examples of very high boiling points. Okay, one more question, and I'll see what else you guys are thinking, or what you guys are thinking about. Abdullah asks, I have a question about electronegativity. Like, what is the electronegativity between OC and OCl2? Do we have to multiply the electronegativity by 2 or just consider it 1 atom? Great question. Let me open up a new, let me do another blank screen here. Don't mind the notes in the background, guys. I'm just using this so I can have a blank screen. So the question was, sorry. Actually, here's what I'll do. I got a plan. Make my life easier. All right, so the question was OCl2. Now, OCl2 would look like this. And it doesn't really matter what it looks like, but this will help me. So Abdullah, not Ahmed, Abdullah Ahmed asks, what about the polarity? Well, one, this is definitely a polar molecule. And how do I know that it's a polar molecule? Well, it has lone pairs on the central atom. So it's definitely polar. But Abdullah is not asking about the molecule. Abdullah is asking about the electronegativity of the bonds. So when I'm looking at the Cl and oxygen bond, what I do is I calculate the difference in electronegativity. Now, I don't know this. I don't have these numbers memorized. I used to back many years ago. So what I would do is go to my lovely friend, the data booklet, and I would scroll all the way down, and I would look at O and Cl. I went a little too deep in my zoom in there. So, okay, so O has an electronegativity of 3.4. Cl has an electronegativity of 3.2. That's what these numbers in the corners mean. That's electronegativity. So O is 3.4, Cl is 3.2. So let's go back to my notes. That means I would take 3.4 minus 3.2. It would be 0.2. I do not, let me pick a different color here. I do not multiply by 2. Again, Abdullah Ahmed asks, would I multiply it by 2 because there's a 2 here? No, 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 no. Just leave it. You don't multiply by 2. You're only looking at one bond. We don't care that there's 2 of them. So if you had to calculate the electronegativity difference between Cl and O, it would be just 0.2. I don't touch it. I don't multiply it. Nothing like that. Whew. Okay, guys. Any more questions? Honestly, guys, if you do have questions, it's a little late. I can keep going, no problem. But maybe what you guys might want to do is tonight or tomorrow actually try to study some things. And then any questions you have, send me an email and I can answer the email, or we can have a Zoom meeting to discuss it. But I am around if you guys have more questions right now. So how you guys doing? What do you think? Thank you, Abdullah. Thank you very much. If you guys want to go, I'll put this recording. This class was a little bit better than my last class, so I'll be putting this recording up on YouTube right now. So give me like 10 minutes, and this will be up on YouTube. Thank you guys for everything. You've been a fantastic group. Everybody, like your group, section 2, and my other chemistry section for hydrocarbon chemistry, you guys have all been so good. All right, so Mohammed has a question. And again, if you guys want to go, you are free to leave. But Mohammed has a question here about reactions and balancing. That's a very open-ended question, isn't it? Well, okay, Israel, like honestly, this class is way better than my other class, but I could put up both videos. But I wouldn't, if I were you, I wouldn't watch both of them. Like, trust me. Everything I did in the other class, I answered in this class and more. So I would probably stick with this video. It's way better. Just trust me on that one. Okay, so again, you guys feel free to leave. You can leave right now. Don't worry about leaving early. But Mohammed has a very deep question that I'll have to explain. He wants to know about reactions and balancing. So if you have to go, thank you very much for coming. You guys have been such a pleasure. And I mean that. You're a fantastic class in such a weird time of COVID and Corona and everything like that. So you guys have all been fantastic. I'm going to open up reactions to help anybody who wants to learn a little bit more about balancing or types of reactions. So Mohammed and anybody else who's interested, I'm going to close some things here so my computer doesn't die. just let me get a drink of water or something, or like a tea. I have some tea made. I just need something to drink here, and I'll be right back. So just give me like literally 2 minutes. I just have to pour up some water or something. I'm so thirsty. So I'll be back. Just give me 1 minute. I'll be right back. Okay, I am back. All right, here we go. Now, so Mohammed, this is a big question, right? Like, how do we balance? How do we predict chemical reactions? Huge question. So I'll try my best to kind of summarize this. I mean, this literally took weeks or like classes to look at. So actually, maybe what I should do is maybe we should, instead of looking at the notes, why don't we look at a worksheet? I think that'd be better. So let me open up a worksheet here. Oh my gosh, you guys, you don't like, I think I have like 50 windows opened up or 50 tabs opened up on my computer here. All right, so let me open up a worksheet here for you. I'll share my screen, of course. Just give me 1 second. All right, so let this load here. Obviously, I'm going into your course, and I'll go to content. And worksheets, and we'll pick unit 5. Now, I don't know which worksheet is which, so let's just try this one. I'll pick a random one, 2.17. Let's see if this is balancing. Yep. So here you go. This is a very good worksheet. This is a lot of practice on balancing. So this is worksheet 5.2.17. This obviously is shared online with the answer key. So I don't know. Let's look at one. Let's look at the top one. Why not? Let's do A, right? Why not? Okay. So balancing chemical equations. This is a tough thing to teach because it's not, there's no formula I can give you. There's no like mass over molar mass. There's no tricks I can say other than it's like solving a a puzzle. The tools that you have to solve this puzzle is that you can put numbers in front of chemicals, but that is it. You cannot change chemical formulas. You can't change elements. You can only put in what we call coefficients. Coefficients are the numbers in front of these chemicals. So coefficients here, typically in chemistry, your coefficients are like 1, 2, 3, 4, 5. And your goal is to get the left side equal to the right side and to make sure everything is balanced. So you can ignore my dog there. She'll calm down in a minute. So on the left, let's look at this element by element. I have one lead and one lead. Okay, so the lead seems to be pretty good right now, the PB. Let's look at another chemical. I have, okay, well, this is an interesting one. I have 2 nitrates, and I'm going to think of this like one chemical. So this is nitrate, and I have 2 of them. But over here, I only have 1 of them. So there's a problem there. I'll worry about that in a minute. The lithium, I have 2 lithiums on the left. I only have 1 lithium on the right. And then my sulfur, everything is good. I have 1 and 1. So I'm seeing some problems here. I'm seeing that lithium isn't balanced and this nitrate isn't balanced. But this is actually pretty easy because if I have 2 lithiums here, well, why don't I put a 2 right here? Now think about that. Look at what just happened to this reaction. The nitrates, I have 2 on the left. Now I have 2 on the right. So everything is balanced here. So I have 1 lead, I have 2 nitrates, I have 2 lithiums, 1 sulfur, 2 lithiums, 2 nitrates, 1 lead, 1 sulfur. That was actually a pretty complicated one. Let's go down to F. Let's have a little look at F here. So F is S8 sulfur. Somebody asked about sulfur earlier. Added to oxygen, and we get SO2 gas. Well, I need to balance this out element by element. This one's a really good one. I think this one's pretty easy. So I have 8 sulfurs and 1 sulfur. So what I'm going to do is I'm going to put an 8 here. Now on the left, I have 8 sulfurs, and on the right, I have 8 sulfurs. The problem is I just really messed up my oxygen. By putting an 8 over here, I've now made 16 oxygen, so really, really messed up. So in order to get 16 over here, I'll put an 8 in front of him. And now everything is done. I have 16 oxygens, I have 8 sulfurs, everybody's happy. All right, any questions on balancing before I get into reactions? Mohammed, how do you feel about that?
Sir, so basically it's just making them equal on both sides. Like we have the same amount of elements on each side of the equation.
Yes. Yep, that's literally what balancing is, making them
Oh,
equal on both sides.
that's simple.
Yeah,
Thank you, sir.
it's simple, but you just take your time. Like when you guys are doing your final exam, take your time. Don't rush, because it's simple, but it's easy to make a little mistake. Okay, so
Mhm.
let's look at reactions and see how you're doing. Okay, this is good. This is a really good worksheet. This worksheet here, 5.2.2. So this is the next worksheet. This is a good one for practice. Now, I can't do everything on this worksheet, but I'll try my best. Let's look at, well, I mean, A, B, and C are really good examples to look at. Okay, so let's look at A. Well, actually, first, let's read the question. Complete and balance the following reactions with the proper states for each product. So when I say states, I mean solid, liquid, gas. And also it wants me to list the reaction type. This is probably one of the hardest worksheets of all of the worksheets, and definitely one I would practice. So this reaction here, this is a compound and then there's an arrow. What this means is this has to be a decomposition. There's no other option. I'm not mixing 2 chemicals together. I'm not combusting this in the presence of oxygen. It is one reactant with an arrow. One reactant with arrow means decomposition. And actually, wow, I picked the hardest one to start off with. This is a special type of decomposition because it has carbonate. Um, you can thank another student in another section for this. The Iman is a student I have in section 1, and she kind of gave me a really good way to explain decompositions with CO3. This is straight from your notes. Carbonate decomposes a little more special than other gases. So let me show you what this would look like if it was a normal decomposition. Normally, I would just split this into elements. So I would get magnesium and I would get CO3 and everybody's happy, right? But that's not how carbonate works. Carbonate is special because it turns into a gas. So carbonate, I would get MgO plus CO2. And that would be my gas here. This one, you guys need, it's straight from your notes. You need to look this up. Whoops, okay. MgO, if you look at your solubility table, this would be a solid. All right, cool. So what about the next one? Cl2Ca. The reaction type of this would be combination. meaning we're putting these elements together. And this is just like in Unit 3 when you did naming. I would put these elements together. CaCl2 would be my chemical compound here. Now you'll notice that I have a solid being mixed with a gas, so there's no water here. So this would be solid. I don't need to balance anything here. Now question C would be what's called a single replacement. A single replacement is when one element tries to replace another element from a compound. So what I would do when I see a single replacement is I would open up my data booklet. Okay, and I would go to this table of single replacement things. I love your data booklet. So this is page 5, and page 5 says the activity series of metals is used to predict the products of single replacement reactions. An element higher on the list will replace from a compound any element below it. So I'm going back to my notes here. I'm looking at aluminum to see if it gets replaced with iron. So my question is, does aluminum replace iron? All right, well, I go back to my data booklet. If aluminum is higher than iron on the list, it will replace it. So aluminum is here, iron is here. Aluminum is higher. So that means that this single replacement reaction will happen. So I go back to my notes. This will happen. Whoops, I didn't mean to do that. So this is single replacement. Aluminum will replace the iron, so I get aluminum iodide. Now I need to balance that chemical equation. Aluminum is +3, so iodide would be 3 here. And then I get poor old iron all by himself. Now there's 2 things I need to do with this question. 1, I need to balance it. And 2, I need to look at the phase. So to see if this would be solid, liquid, gas, aqueous, what. So I'm looking at ALI3. I'm going to share my data booklet again. So I go to my solubility table. Okay. Most compounds that are bonded to iodine are soluble, except for these. So chromium, copper, silver, gold, mercury, etc. But aluminum isn't there. So that's all good. I go back to my notes. I know it's a lot of like switching back and forth, but there's really nothing I can do here. So sorry, let me share my screen. I'm not going to go back to another slide again. It's getting too much going back and forth. So this is single replacement. I get my aluminum iodide, which is 3, plus my iron solid. Now this was aqueous, which I just checked on my solubility table. So the last thing I need to do for full marks here is to balance this. So this is actually a good one to balance. So I want to put a 2 here to turn this into a 6. So then I'll put a 3 here, and then I need a 2, and I need a 3, and that one's balanced. That's a tough one. Actually, A and C in this worksheet were tough. All right, guys. I mean, it's 5 o'clock. I think I'm going to stop here. But if you guys have any more questions, maybe you want to send me an email or something. I do have another question from Abdullah. Sorry, I'm just reading. I got a lot going on in the chat here. Hold on. Okay, so Israel, I don't really know how to answer that. Your test should have feedback for you on D2L. So like whatever's there, that's all we can do. I mean, it's Thursday at 5 o'clock. I can't do anymore. But Abdullah, I can definitely do this question. I can show you a total or net ionic for sure. And Israel, I don't know what to say about your test. It is what it is. So let's look at net or total ionic equations. And then that's it, guys. I got to stop after this. I've been doing this since 10:30. So any more questions you have after this, just send me an email and let me like get some dinner and I can answer it later. So let's look at net and total ionic. I just got to find out what worksheet it's on. It's probably in the last worksheet here. How many moles? Okay, it's not on that worksheet. Hold on, I'll find it. I just got to pick the right worksheet. Let me try this one again. And I'll try this one. See if I can find a net ionic equation. Nope. Sorry, I'm just looking for one here. Sorry, guys. I can't seem to find one. If I can't find one, we'll just do it from our notes. Okay, and here we go. I don't know why I didn't open this one. So section or worksheet 5.2.3. Here you go. This is a good one. So I'll just do one of these and then I got to go. All right, so let me share my screen and we'll have a little look at this. Oops. Okay, so this question says, write the total ionic and net ionic equation for each reaction below. So what you would do for the total ionic is, oops, get my pen here. Anything that's aqueous, you write as ions. So Fe solid plus 2Ag plus. Because it's aqueous, I split it. Oh, hold on, I'm going to definitely run out of room here. Let me just start that one over. I got a little... I wasn't thinking forward in the future for this. So Fe solid, okay, that stays the same. It's not aqueous. I add 2 silvers. That would be aqueous because the chemical is aqueous. I add 2 nitrates. Okay, I get 2 silvers and I get my iron, which is again aqueous because the molecule is aqueous. And NO3, I get 2 of these. There you go. That's aqueous. Sorry, I kind of ran out of room there. Whoops. All right, so there is my total ionic equation. Now, what you do when you're wanting to write the net ionic equation, you cancel any chemicals that appear on both sides. So my nitrates are gone. You'll notice nothing else is the same. They're solids, they're aqueuses, they're not the same. So once you've canceled your spectator ions, you just write what's left. Okay, I'm not thinking, I'm just literally writing down what's left. There's nothing I need to add here or do here. All right, so there you go. That's it. That would be the total ionic equation in the blue and the net ionic equation in the red. Oops, this should be Fe2 plus, not F2 plus. All right, cool.
Master?
Yep.
There is a question like this in the final?
Yes, yes, definitely. You will definitely see a total ionic and net ionic equation on the final, for sure.
Okay, thank you, Mr.
No problem.
Thank you for your time, Mr.
Yes, no problem. Thank you very much for paying attention and sticking around with me. All right, guys, I'm going to go. Have a great evening. If you have any questions in the next, couple hours or tomorrow, just send me an email. Even if tomorrow, if you want to have a one-on-one Zoom meeting, I'll be around after the morning. So just send me an email. And yeah, good luck, guys. I'll see you in your exam. I'm in the gym with you, so I will see you all on Saturday. Thank you, Abdullah. Thank you for the kind words. Thanks, everybody. I'll have this up on YouTube in it'll take a little bit of time for YouTube to render, like to upload the video, but it will be up tonight. Thanks, Mohammed. Thanks, everybody. You guys have been a good group. I will see you soon. Goodbye. Thanks again.